Hello community! Today we're going to talk about graph machine learning, and I have one single message. Be careful if you cut your graph. Why am I telling you this? In my last video, when we were encoding node embeddings in PyTorch geometric, we used the command torch geometric transform dot random node split. And what it did, it was very easy. We had our homogeneous data and our heterogeneous data. And then we just had to, for the training of the model, we had to split up the training data set, and we did it with this command, random node split. You see here our functional transform, the decorator for our functional data pipeline. Each data pipe can be registered to support the functional invocation. And what it did, we have a node level random split into a training mask, a validation mask, and a task mask attribute. And this all goes to the data, either the heterogeneous data object or the homogeneous data object, depending on what model you're working with. Beautiful. Next step. So we have here our structured data pipeline, the data pipes coming in. We have structured streaming data coming in continuously, filling up my data set. And I use this data set for graph machine learning beautifully. So what we do, we separate the datas in a training data set, a validation data set, and test data set. But here happened my mistake. Now look, this is a graph. You know it. This is simply a node and an edge representation. And the distance you see of the edges in no way is there a numeric distance, because mathematically this is not a space where a distance function is defined. This is just some configuration of nodes and edges, and this is it. This is the reason why we need representational learning for graphs. Beautiful, because what we want to find a representation, a node embedding, for example, that gives us some information of the structural information of the graphs and of the, let's say, feature tensors that are attached to each node and each edge. So here we go. Let's look here at these two nodes in specific. We have at first here the yellow node and its epsilon surrounding. We have here a green node. But remember, this is just from a graph data that has not been performed a normalization or anything at all. And the space itself is not a vector space. Great. Just by accident, those two nodes lie within an epsilon surrounding here of each other. So what we do? We have attached with the yellow node, of course, a node feature tensor. Imagine this yellow node is a book. It represents a book, and the node feature tensor encodes the semantic content of all the 400 pages of this book in a huge node feature tensor. I showed you this, how we do this, either with SBERT or with some other sentence transformers in my last video. And of course the green here is another book, let's say in another language, and we do a node feature tensor calculation, and we calculate now a numerical feature tensor for this particular book. So we have now a comparable tensor structure. Now you might ask, okay, now that we have tensors, but what is close? What does close mean? Well, I'm so glad you ask, because you remember our initial condition, and we are here, let's say, in a physical simulation. And when we start the system, our very first step, the zero order of our probability, is that we say we put our feature tensor as the starting ground for our node embedding. This is somehow we have to start, and this is the way we start. And you say, hey, great, can you show me? Yes. Let me give you this beautiful lecture by Professor Yuri Leskovich. This is lecture 17.4. This is, hey, I have to say something. This is on YouTube. You go Stanford Online, and you go here for Stanford CS224W. And you get a playlist of 60 videos. And if you have a look at these 60 videos, take a week, and you will understand about graph neural network a lot of. But just to show you, he sets the input node embedding, the age of the node V, at the zero level, at the very first beginning, equal to x of v, where x of v is for all v element of our vertices is an input node feature tensor or a vector, to make it easy. Beautiful. So now we can go. So we know that this space here has no metric at all. It is not a vector space. And we have to construct now, with node representation learning GraphML, we have now to construct our space. You remember in the last video where we were talking about node embedding, and I showed you the calculation in PyTorch geometric, we were talking about the transfer of our pure data into a computational graph, where we can apply GraphML algorithms. Again, we have the node and the node feature tensor, we have an edge and an edge feature tensor, and all this has a structural information we have in our adjacency matrix of the graph. But now if you want to apply message passing formalism for a better node embedding, for the next level node embedding of our node N0, our red node, we see how many nodes can we get if we just have a one hop neighborhood jump. So if we go just one from N0, we have N1, we have N2, and we have N3. These are the three nodes I can reach if I go from N0. And those three nodes I take now in the one hop environment. This is what's happened on our GNN layer 1. And we ignite that each node generates and sends out a message along the edge. I showed you the mathematical formulation in the last video. And all three different messages are aggregated now before this is the new input. It encodes the structural information of a one-hop neighborhood with all the necessary information, plus the message of the node N0 itself. If it has some valuable information, we aggregate this, and you showed your graph convolution network or the graph SAGE or graph attention networks. This is the content of my last video where I showed you how to construct this. And if you do then your programming, you build a GNN model, and we have different layers, and we stack those layers together. You see that here in the first layer, we have exactly this mechanism for a better node embedding, a next level node embedding of our node N0. We apply exactly this message passing mechanism. And for all the other nodes, if we stack different layers, you see here, if you apply this layer, you just go exponentially up, and it becomes computational very challenging if you have several layers with multi-million nodes. So, doing now the first GNN layer computation, and we include the information for a new node embedding, you see that from the epsilon surrounding of our yellow node, suddenly the green node left epsilon. Because it's the green node now included also its information on one hop, and this is just for one hop, it's just connected to this pink node here. So it came closer in a better node embedding closer, and it left here the vicinity of our yellow node. Beautiful. This is exactly what we wanted. Because now, if we construct a vector space in the very first approximation, we get now a notion of distance. And with this notion of distance, you are happy, you are excited, I know this. But we are here in graph representational learning. We include now in our very first step the environmental information of the epsilon or one hop or two hop neighborhood jump. We are the mechanism of message passing to calculate a new node embedding. A node embedding for the yellow node, a node embedding for the green node. And in both cases, a node embedding, we are operating in a vector space, is of course a vector. Now, if I told you we have a feature tensor, high-dimensional feature tensor, including the complete semantic content of a book, of course we have here, instead of a vector, we have a tensor high-dimensional object, and we're operating in a high-dimensional tensor space. Anyway, but you have to understand, this is done after we apply the GNN layer calculation. But what we do, we take our raw graph data and we separate it in our training data set, the test data set, and the evaluation data set that also has a graph structure before we apply here the transformation to a vector space, before we send the data to our GNN layer model. So therefore, you understand now that your training data, your validation data set, and your test data set, which has also a graph structure, is now, when you cut it, you lose information of the whole complete graph. So the way you cut your complete data set into a training data set, into evaluation, no, training is the big one, evaluation this is here my test data set. Let's encode it. Maybe, yes, we cut it and one huge chunk and two small chunks. So this is our training data set. Let's say this is 75, 80%. And here we have maybe 15% is the relation data set. And here, top left, we have the training data set. Now look at this. And this is a mistake I made because I was not careful enough about the inherent data structure in my three data sets. You see here, and I have just a very simple visualization. Please imagine a more complex object. That here we have this node where we have a lot of green node types. Each color is indicates a different node type. So let's say this pink is a car and green is a book. And this light rosa is, I don't know, a human, a person. So a person buys books, beautiful. But you see here, this is an inherent subgraph structure in our training data set. And I trained my model on this major structural information in my training data set. And when I did the evaluation, because in my evaluation data set was a similar structure, also I achieved quite a good evaluation on my model. But the horror happened when I did the test with my test data set, because then suddenly the model underperformed horribly. And you see why? Because as a simple visualization, but you get the idea. Here, I do not have the green dot substructure, subgraph that I have in my other two data set. So the inherent structural information of this cutted test graph, subgraph structure, was missing a particular structural object the other two datasets have. And this is the mistake happened to me, and I could not explain it. So again, just to make it visible to people, this is here the data structure in our training data set. This is the training structure in our evaluation data set. But you can clearly see here in our test data set, we are missing this particular structure. So, beautiful. Here we go. I thought there's an easy solution. I do not cut the data. I just look at it at different time slices. So what I did, I took 4 days, all data, everything in from my structured streaming data, and I said, this is my training data set, my 80% data set. And then the next day or next hour, whatever you prefer, I took another complete data set of this day in, and I said, okay, this is my evaluation data set. And you get it, the next day, and it was the day before Christmas, I took in this data, and it was my test data set. Now, interestingly, analyzing those 3 different subdatas, I noticed that this graph had, how to put this, imagine, this is a credit card data, and you have credit card transactions, and there's one fraud. In this 4 days, there was just one fraud in the data, yeah? And then on this next particular day where I did the evaluation, there was a factor 10 less fraud. There was just 0.1 fraud cases happening in my data set. And then close to Christmas, you're not going to believe it, in the credit card transformation data, suddenly there were 12 fraud cases in my test data set. So you see, it was not in any way that you could say this is kind of a coherence or homomorphic, whatever you will call it. The mistake I made, I did not verify my training data set. I did not have a look at the training data set for the structural information from the coherence of the structure to my validation data set and to my test data set. So my lesson learned is, whatever you do, have a look at your training data set, analyze your validation data set, and maybe do some data exploration analysis on your test data set, just to be sure that the dataset you use it, if you cut graphs, you can lose valuable information, and maybe this is exactly what you are looking for. And if you have a training dataset, let's say where you have, I don't know, 10 fraud cases in your credit card transactions, and you train the model on this, and you have a validation dataset also with 10 fraud cases, yeah, then you have the model trained with 10 fraud cases. And this is not what you want, because you want to detect every single fraud case that's happening. So take care about this. You know, with the validation dataset, if the training dataset accuracy goes up and your validation dataset accuracy goes down, you have a problem. And the same as training dataset goes up and the test dataset accuracy goes down. Those are the two scenario overfitting, and you know everything from machine learning from the normal non-graph dataset, but especially with graph, I found it interesting for me where my error was, and I hope you learn a little bit so that you are happy like her if you follow my advice, if you have then 3 coherent datasets where the structural information that you encode in all 3 different datasets is comparable, and that your graph machine learning model, that your representational learning of this very, very complex graph data, if you work with millions of nodes and millions of edges, that you are successful. And I hope you found this video helpful, and I would be glad if I see you in my next video.